Hello, after getting acquainted with the calculus of vector and scalar fields, let us discuss the fundamental laws of electromagnetism. These laws were given separately for electrostatics and magnetostatics. Before Maxwell, these two fields were thought to be separate fields with no correlation with each other. But Maxwell realized similarity in them in terms of their behavior and nature, and he unified these fields into one, the electromagnetism. The four basic equations based on laws of electromagnetism after Maxwell's work were named as Maxwell's equations. Before starting the lecture, let me tell you how in novice perception one can see similarity in electric and magnetic fields. To find the electric field and magnetic field induction, you have two laws, namely Coulomb's law and Biot-Savart law. They read E equal to 1 by 4 pi epsilon naught multiplied by volume integral of volumetric charge density divided by r square, where r is the distance from the source. And magnetic field induction B is equal to mu naught by 4 pi multiplied by line integral of current divided by r square. The form of both the equations for electrostatic and magnetostatic field is similar, with only difference in the coefficient epsilon naught and mu naught and source of respective field. The integrals are in the dimensions in which the source has its span. Before proceeding to our discussion, let us define the flux of a field. A field, electric or magnetic, is represented by imaginary arrows. Denser the arrows, intense the field. The number of arrows passing through a surface normal to them is called the flux of the field attached or linked with the surface. It can be argued that because these arrows are imaginary, one can draw as many of the arrows as possible. So, to calculate this number or the flux mathematically, you find the scalar product of the field and the surface. Since a field is already defined as a function of space coordinates, its intensity varies with the space. So you need to find the scalar product of the field and infinitesimally small area in which the field may be supposed to be constant to find the flux. You may have an electric flux phi E or magnetic flux phi M respectively in the coming discussions. Now let us come to the agenda, the laws. The first one is the Gauss law. As you have already studied it, the Gauss law in electrostatics says that total outward flux, this, of electric field from a closed surface is equal to the total charge enclosed within that surface divided by epsilon naught. Total outward electric flux is given by closed surface integral of electric field, but the integral equations are not easy to handle. They may be converted into differential equations with no alteration in their physical meaning. To do so, we do like the following. We use Gauss's theorem to convert closed surface integral into the volume integral, and we write the total charge in the given volume enclosed by the closed surface by volume integral of charge density. This. The similar operation can be done in magnetostatics also. But as the magnetic field lines are closed, so if a magnetic flux line is exiting the closed surface, it will return definitely to give vanishing outward magnetic flux in the given closed surface. It is written like this, and the closed surface integral of magnetic field can be converted into volume integral of divergence of magnetic field, like we have done in case of electrostatics. Now, by comparison, these two integral equations can be converted into differential equations like this and this. Now, this equation is the statement of Gauss's law in electrostatics, and this is also a form of Gauss law in magnetostatics, and it says that there is no magnetic monopole in the nature. The second law is the Faraday's law. It establishes the connection between electric field and magnetic field. It says that when a coil of wire suffers a change in magnetic flux attached to it by any means, an electromotive force EMF is established in the coil. This is the mathematical expression of the Faraday's law. The negative sign represents that the induced EMF opposes its cause. Now the question is, what is the meaning of EMF? An EMF is the work done to flow a unit positive charge through the whole circuit, including the battery. So this is the work, not the force, as the name indicates. And the work can be represented by line integral of electric field over a closed path. So the EMF is given by closed line integral of electric field. This is the closed line integral because we have to compute the work in the whole circuit. So the Faraday's law becomes the EMF, the closed line integral of electric field, is equal to the rate of change of magnetic flux with negative sign. The magnetic flux is given by the surface integral of magnetic field. So mathematically, this is the integral form of Faraday's law. Now, like Gauss law, we can convert it into differential form. And to do so, we use Stokes' law to convert closed line integral of electric field into the surface integral of curl of electric field. And here, the order of differential with respect to time and integral with respect to the space coordinates can be reversed. Now the comparison gives del cross E equal to minus del V over del T, or the curl of electric field is equal to time rate of magnetic field. Now the next is the Ampere's law. As for highly symmetric charge distributions, we can calculate the electric field more easily using Gauss's law than the Coulomb's law. Similarly, Ampere's law relates the tangential component of magnetic field summed around a closed curve C with the current that passes through the surface bounded by that curve. Here, if there is a current passing through this wire and this is an Amperean loop C, then the tangential component B summed over this curve is related with the current inside this curve. And this relation is the closed line integral of magnetic field is equal to mu naught times the current bounded by the curve. In this law, the magnetic field in the line integral is purely the effect of current enclosed by the Amperean loop. If any other agency is also causing the magnetic field at the same point, then the line integral of it chooses the part due only to the enclosed current. So, in abstract form, the line integral or circulation of the magnetic field around some arbitrary closed curve is proportional to the total current enclosed by that curve. But this form is an integral form where the current can be written as the surface integral of current density. Here the current density is defined as the amount of current passing per unit surface area normal to it. Since it is normal to the surface, it is a vector quantity. You can use Stokes' theorem to convert the line integral at left hand side into the surface integral, and then it can be compared to give a differential equation for Ampere's law. So this is the differential form of Ampere's law, and this is the integral form of Ampere's law. Now these are the four fundamental laws and the differential equations for them before Maxwell. The first equation is the Gauss law in the electrostatics. Second equation has no specific name, but it is the statement telling that there is no magnetic monopole in the nature. Third and fourth equations are the statements of Faraday's law and Ampere's law. In the next lecture, we will study the work of Maxwell and the Maxwell's equations.